Hey folks, in this video we're going to be talking about chemicals, elements, and compounds, and other stuff like formulas. Oh my, it's going to be amazing. So we have a few objectives. I would like you to be able to define chemical as a word. I would also like you to be able to interpret and write chemical formulas. I would like you to be able to differentiate between elements and compounds, and more fun stuff. I would like you to be able to define empirical formulas, and I have a forkload of vocab for you. So why don't you gander all of that for a second and pause it if you need to, but let's get going. So chemicals and formulas. I have a few chemicals down there, now that things obscuring them, and I also have formulas written with them. Well, chemicals are what we call pure substances, or pure substances, I suppose, are what we call chemicals. This means that they cannot be separated into smaller components without breaking chemical bonds. So examples would be like water or table salt or pure gold. If you have good pure samples of those, you can't actually break down them into smaller, different components. And the key here is different components. Like you could take a pile of table salt and take a scoop out and separate it that way, but you're not making it into different components. It's just different piles of the same thing. Counterexamples would be things like sea salt, salt water, or trees and dirt. Salt water, you can take that. You can remove the water either by evaporation or another process, and you can be left with a pile of salt and a cup of water. Or trees, you can separate those into many different components. You could potentially burn it and remove gases and then get charcoal. Lots of different processes there. Dirt, also very complicated stuff that you can separate into many different chemical compounds. So these counterexamples, these are what we call mixtures, when we have many pure substances that are combined together to make something more complicated. And so chemicals, or pure substances, would include elements, which are sometimes called simple substances, things called compounds, and also things called alloys. So if we're going to talk about chemicals, it's important that we're able to understand those chemical formulas found at the bottom of the screen. So chemical formulas are what we use to describe chemicals or pure substances, and they tell us what elements these things are composed of, these pure substances, and also what ratio elements combine in to form these chemicals, because different chemicals are made up of elements in different ratios. And also they will tell us if there is a charge, like on this dude, as we have in ions. So when we talk about a formula, what are we talking about? Chemical formulas. So we have a formula unit, which we're going to use to describe ionic compounds. That is the unit that makes it up, or how we describe it with its symbols. And we also have our molecular formula, which we use for covalent compounds. These both basically describe the same thing, and we'll talk more about those in detail in the future. So if we're going to write a chemical formula, we need to know what it's made up of. Well, the first thing is we always have element symbols. Here we have hydrogen, carbon, and oxygen. Here we have nitrogen and hydrogen. So these identify which elements are in the chemical. The other very important thing that we have are these subscript numbers. Subscript, as the name implies, are sub, like a submarine is underwater. They are these numbers that come below everything. And so what these tell us is how many of the atom is, or a particular element, how many atoms of a particular element are in the chemical. So we know that this compound here is made up of hydrogen, 2 hydrogen atoms specifically, 2 carbon atoms, and 4 oxygen atoms. If they're outside of parentheses, like with this example here, well, what we're going to do is say that that subscript applies to whatever is inside of the parentheses. So in this case, when there's a 2 outside of this parentheses with the PO4 inside, this means that there are 2 of these PO4s. It doesn't mean the same thing as P2O8. If we wanted to, we could just write P2O8, but this tells us that there are 2 of these distinct PO4 groups. So there are also letters that we find in our subscript. These guys, they're in parentheses, and those tell us what the state of matter is for this chemical. This G here tells me that this dude is a gas. And so they'll tell us if we have a solid, liquid, gas, or plasma, which rarely shows up. So that S8 is a liquid because it has an L in parentheses. I wish that guy would stop popping up. The CaPO43 is in the solid state. We know that because there's a little S in parentheses after that. And this dude is in the gaseous state. Well, what about that little AQ? Well, sometimes we see AQ, and that means that this is dissolved in water. That AQ means aqueous, or I've heard some people say aqueous. And so there are also these superscript numbers. We actually don't have any numbers in the superscript up here, but these are used to indicate charge. When we only have a charge of +1 or -1, we're only just going to use a plus or a minus symbol. If this had a charge of +2, I would make this a little 2+ to indicate the charge. So earlier I mentioned that chemicals could be divided into elements, compounds, and alloys. Let's talk about those. Elements, these are, or if I'm talking about an element, this is going to be matter consisting of only one element. And usually elements are going to occur as single atoms or sometimes as multiple atoms bonded together. So here are some examples. Hydrogen likes to occur in pairs. Bromine likes to occur in pairs. Iron is just going to be single atoms that are doing their own thing. They might group together in a larger iron, but they're not chemically bonded. They can be separated out individually. Whereas if we have a big pool of hydrogen, anytime some hydrogen leaves, they're going to leave in pairs because they are bonded together. Compounds are different from elements. Elements are made of one element. Elements are made of one element. Yeah. Compounds are made of multiple elements, 2 or more, that are joined together. So when we have multiple elements joined together, like in these 3 examples here, we have compounds. And so compounds combine in like defined, definite, fixed ratios. So this dude here, H2C2O4, this chemical always combines in this ratio. NH4 plus ammonium ion always combines as NH4 plus. And so we have ionic compounds and also covalent compounds. And they are different because ionic compounds are held together because they are made of ions with opposite charges, and those opposites attract, kind of like magnets, and hold these ionic compounds together. Here we have an example of an ionic compound with our calcium and our PO4. These are both ions, and they hold together like magnets. We also call ionic compounds salts. Just like pretty much any ionic compound, we can be like, yeah, it's a salt. It's salt. It's a fun buzzword. So there are also covalent compounds, which are most of the things that I've shown down here. And covalent compounds are held together by atoms sharing electrons. As opposed to them being held together like magnets, these atoms are sharing electrons so that they can become more stable, as it turns out. We also have alloys, which we're going to talk about less. And alloys are similar to compounds, but they generally contain a metal and are defined by approximate ratios as opposed to these other dudes. Alloys are really important though, like steel is an alloy, and many of the metals that we interact with in our lives are alloys. You can mix elements together to make metals stronger or have different properties. Alloys are cool. I'll rant about them some other time. When we talk about elements, it's important to differentiate our monoatomic elements and our diatomic elements. So monoatomic elements are elements that occur as a single atom, as I alluded to before with iron. This is most of the elements on the periodic table. Most of them are fine just being an individual atom, and they're like, yeah, I'm gonna do me. And these elements usually are gonna combine out in nature. It's uncommon that we'll find isolated atoms, but you know, it's theoretically possible. Somebody did that recently. There was a cool experiment. They're like, we got a single atom suspended in this laser beam. It was very cool. So diatomic elements, on the other hand, are elements that always occur as pairs. You might think of them as sort of codependent compared to the fiercely independent monoatomic elements. These atoms are covalently bonded together, so they're sharing electrons. They're dependent on each other. And here's a small list because there are not too many of them. We've got hydrogen, nitrogen, oxygen, all of the halogens. That's it. Those are our diatomic elements. And so we can see them arranged, I guess not all the elements, all the halogens. Astatine's not on the team. AT. We rarely talk about astatine. So if we look at them, I remember this by saying, all right, it's hydrogen, and then we've got kind of this like thing there. If you like mnemonic devices, one I've heard is never or have no fear of cold beer. Mnemonics don't work for me, but some people love them. So it's have no fear of cold. Oh, ice cold beer. See, I suck at mnemonics. Have no fear of ice cold beer. It names all of them. I don't find mnemonics helpful, but you might like this. H for hydrogen, N for nitrogen, F for fluorine, O for oxygen, I for iodine, C for chlorine, B for bromine. So let's talk about covalent compounds and ionic compounds, because compounds are great. If we're talking about covalent compounds, we're going to be talking about molecules. This is the name for the small single unit of a covalent compound. When we break covalent compounds into their individual units, the smallest unit we can get is a molecule. So atoms are related to molecules, as gold is made up of many, many, many atoms. If we have a sample of sugar, it's going to be made up of many, many molecules. Those are the smallest unit. As I said, a piece of gold is made up of many gold atoms. A piece of sugar is made up of many sugar molecules. And so here we can actually see an image of what a gold sample of gold might look like. It's all these little balls or spheres, gold atoms packed tightly together. And actually people have looked at gold with super crazy instruments. I believe these are probably atomic force microscopy, but it also might be a tunnel electron microscope. I don't know. Either way, this is like on the scale of nanometers, and you can see these are little gold atoms, and they arrange kind of just like they arrange in there. You don't have the three-dimensional effect, but you can see the layering. Very cool. On the other hand, here is an image of a sugar crystal. These are how sugar molecules arrange in a crystal. This is our individual molecule, and we can see there's many other versions of this. They're twisted and oriented in different directions, but a sugar molecule, or a sample of sugar, is made of many of these molecules arranged in this fashion. Neat. So every molecule in a pure sample is like identical. They're all completely identical. They should all have the exact same molecular formula. And I should go back. You may have different isotopes in your sample, but you can also have theoretically a pure sample where all the isotopes are the same. And so really the key takeaway is that all the molecules in a pure sample are going to have the exact same molecular formula. So when we talk about molecules, they're going to be made pretty much exclusively of non-metal elements. If you're getting into some fancy chemistry, you might find some exceptions. But for us, our molecules are going to be made of completely non-metals, and they're going to be held together by these atoms sharing electrons. And so molecules can be really small, like hydrogen molecules, H2, or water is H2O, or they can be massive, like proteins, which are made of hundreds or sometimes thousands of atoms if they are giant proteins. And so on the other hand, if we're talking about ionic compounds, we have these things called the formula unit. That is the name for the smallest unit of an ionic compound. And so these are kind of like Legos. That's the way I imagine it. But every piece is identical. So imagine you've just got like a gajillion little 2x2 Lego bricks. And they're all black or blue or whatever your favorite color is. And so we kind of just stack those up to make a ionic compound. So if you have a piece of salt, it's like a gajillion little salt Legos constructed together to make a nice little grain of salt. And so these are held together, as I said before, by the opposite charges of those ions. We have a cation, a metal, that's formed a cation, and a non-metal that's formed an anion, and those opposite charges hold together. And so formula units are generally much smaller and more simple than the molecular formulas of covalent compounds. Cool. So let's talk a little bit about empirical formulas. These are some interesting things. It's basically a reduced version of a molecular formula. The ratios in the element are reduced to the smallest integer or whole number values possible. And so we're only going to use this for covalent compounds because this is already done in ionic compounds, always. And so some examples, let's look one here. So here, this is my formula for glucose. I could reduce this to the empirical formula of CH2O. So I would divide all of these numbers by 6 to make it 1 to 2 to 1. Or if I had N2O4, I can reduce this to just NO2. Divide both of these subscripts by 2 and reduce the ratio between them. Sometimes the empirical formula and molecular formula are going to be the exact same thing. So like for water, I can't reduce these and still have whole numbers. Yeah, it's a 2 to 1 ratio. Or here's another fun molecule that we're not going to name. But since there's only one oxygen, I can't divide that down and reduce those other numbers without chopping that oxygen in half, and I wouldn't have a whole number then. So empirical formulas, we'll talk more about them in the future. Here's a snake in a hat. Here's another snack in a hat. Here's a very fancy cobra in a hat. Anyway, let's do a little bit of practice. Here's some problems. I want you to pause the video and think about these, and we'll go through them together. Sweet, you paused the video and thought about them. Let's talk about them. So which of these is an element? Remember, an element is composed of only one element, and nitrogen is the only thing out here that is not a combination of different elements. So N2 would be our element. Which of the following is a formula unit? Well, remember, formula units are for describing ionic compounds. And ionic compounds are a combination of typically of a metal and a non-metal. And this MgBr is our only example where we have a metal. All of these other elements are non-metals. So this must be our formula unit. Which of these is an empirical formula? Well, remember, an empirical formula cannot be reduced, and it only applies to molecular compounds. These two dudes are ionic, so we're not even going to consider them. This formula can be reduced, This one cannot. I can't divide that 3 down and also this 8 without losing those whole numbers. So this would be our empirical formula. And which of these is not anionic compounds? Well, I'm going to look and find the compound down here that is made of only nonmetals. Because remember, if you are made of only nonmetals, you're probably ionic. Although I should clarify, we're looking for, something that's not a metal and nonmetal. And so that would be CO2. That's our only chemical down there that is made of both nonmetals. So there we go. Sweet. Well, that is the end of this video. I hope you understand. I threw a lot at you in this one. It's kind of long, so we're going to wrap it up quick, and I'm just going to say ta-ta. Have a great rest of your life.